Alright class, the last lesson we're going to do today is rational and polynomial inequalities. The polynomial ones are just like the quadratic ones. First thing you need to do is find your zeros by solving and setting equal. Once you have your zeros, then you plot them on the number line. Remember to make an open or closed circle depending on the inequality symbol. Alright, so based on the inequality symbol, and then finally you have to test each interval. And again, we did this with quadratics, but now we're doing it with any polynomial, so this could be cubic, quartic, quintic. So to find the solutions. Okay, so if we look at, so you can pause the screen and write that down. If you look at the first example, we need to factor it first. First thing I see is we can take an x out. Now, this is more factorable, and you can use synthetic division to do it. I'm going to just use the pattern that I know. I wouldn't expect you to know this pattern, but I wouldn't worry too much about it. Now here's the thing though, this quadratic will not give you real answers, so you can't even use those as zeros. We really only need to use the x equals 0 and x minus 1 equals 0, so x equals 1. So now you're going to make a number line, and we're going to put 0 on, as well as 1. And they're both going to be open circles. And so now we're going to test. So I'm going to use -1, I guess 0.5, and 2. And all you do is plug these into the, I like to plug them into the original and see what signs you have. So if I put a -1 in, that becomes a positive 1, because it's negative to the fourth. And then minus another -1 is still positive, so this is going to be a positive solution. When I put 1/2 in, when you raise 1/2 to the fourth power, it's like a very small fraction. What is it? 1/16. And then minus 1/2 will be negative. And then if you put 2 in, you're going to get a positive value again. So then you just have to see which one you want. And if you look at the statement, you want greater than 0, which means you want the positive ones. So that means the solutions, or the solution, I'll say solutions, are the intervals from -infinity up to 0. And again, they're open circles, so we're not going to bracket them. And then we're going to go from 1 to infinity. Okay? And again, you should remember that we did zeros. All of these have multiplicities of 1, which means they should cross at the zeros, which means they should change sign each time, if you look at it graphically. Let's look at number 2 then. Number 2 is already factored for you, which is kind of nice. So all we have to do is put our zeros on the number line. There's a few of them. So we get x equals -1, x equals 3, and x equals -4. So you want to start with the most negative, and then -1, and then 3. So now that we're going to test these, I'm going to use -5, maybe -2, 0, and 4. And then I'm just going to kind of plug them in and again see what happens with the signs. So this would be negative when it's -5, negative, and this is always going to be positive. So negative times a negative times positive is positive. Oh, I forgot to also put open circles on all these, just so I remind myself that it's not equal to. -2. When you put a -2 in, that's still negative. That's still negative. That's still positive. So it's positive again. Now before we move on, notice how it didn't change signs here. This is the first time we've really seen this, and it should make sense because if you look, that's at -4. That's this factor right here. Notice how it has a multiplicity of 2, which means when it hits -4, it's going to bounce back in the direction it came from. So it was in the positive, it bounces off the 0, and it's still positive. So that's where the multiplicity comes in. And actually, you could do these with multiplicity. Since -1 is a multiplicity of 1, it should change signs. And then at 3, since it's a multiplicity of 1, it should change signs back. But let's double check in case you don't want to assume. When I put a 0 in, you get a positive, a negative, and then a positive. So that would give you a negative result. And then when you put a 4 in, everything's positive, so it's positive. So it did work out. And now we can just write our solution in interval notation, but before we do that, we have to figure out what we want. It says I want everything that's greater than 0. Greater is positive, so we want all of this. But you have to be careful about this. We don't include negative 4. So we go negative infinity up to negative 4, and then we start at negative 4 again and go up to negative 1, and then we start at 3 and go to infinity. So this would be my solution set in interval notation. Okay, so now we're going to do this with rational inequalities. Same thing. There's really only one extra thing you have to worry about. Well, two things. First, again, you have to move everything to one side. So the other side's 0. Kind of like the other ones that we had set up. Then for number 2, you have to find your zeros again. And again, this will come from the numerator when you have a rational inequality. So you set the numerator piece is equal to 0, and then it's open or closed again depending on symbol. The symbol determines open/closed. Now here's the thing you have to remember though. With rational inequalities, rational functions, what I was saying was that remember when you have a rational inequality, you have a denominator, and we get vertical asymptotes from that denominator. And remember, if they're odd, that they go all the way up, and then on the other side of it, they're at the bottom, which means that at undefines, we can also switch between positive and negative. So because of that, we need to find the restrictions, which are in the denominator. Now, since they're just restrictions, they are always open circles. That's the key. So anything you get from the denominator, the unknowns or the undefines, you have to have open circles at those, even if it's greater than or equal to symbol. And then finally, we do what we did before, test the intervals. So let's see that in practice. Again, pause the screen if you need to write that stuff down, and keep writing. Example 3. I need to find my zeros, and again, my zeros come from when you set the top equal to 0. So I have x equals negative 2 and x equals 3. And I also have undefines. It's undefined at x equals 1 and x equals negative 1, and this has a multiplicity of 2. I'm just going to note that. Alright, and everything's going to be open circle because it's not equal to. So my most left point is negative 2, then negative 1, then 1, and then 3. And then we start testing the interval. So again, I do sign charts. I make x equals negative 3. If you plug that into here, you get a negative, negative. This will be a negative squared, which becomes a positive. This will always be positive. So if you look at this, you end up with a negative total because there's 3 of them. Now, since it's an odd 0, it should be positive in between here. Okay, so you can kind of use that information to help you out. So negative 1.5, that now becomes positive. I'll do it down here. So I have positive, negative, over negative, and this will always be positive. So this will end up being positive like we thought. Now at negative 1, we have a vertical asymptote, and it has a multiplicity of 2, which means that it should stay positive. So if I put 0 in, I get positive, negative, negative, positive, and sure enough, it does stay positive, like we thought. If I put a 2 in between 1 and 3, we get positive, negative, positive, positive, so that goes to negative. And then if we put a 4 in, everything should be positive. So this is my my sign chart. Again, all of these should be open circles. I always am forgetting to put those on there. And again, we want greater than 0, so we want all the positive pieces. So I want this interval, this interval, I want this interval, this interval, and this interval. So I'm going to do that in interval notation. Negative 2 to negative 1, union, negative 1 to 1, union 3 to infinity. Alright, so we have one more quick one. Well, actually, maybe not that quick. This one is a little challenging because we have to get it equal to 0. If you notice, this one has a 3 on this side. So the first thing we have to do is move that over. And when you do that, we need to get a common denominator to push these together because we can't analyze this unless we do that. So since this is an x plus 2, we're going to put x plus 2 on the bottom and multiply by an x plus 2 on the top. Now I can push these together because they have the same denominator. There's an x plus 2 on the bottom. I have a 4x and a minus 3x, that's x. I have a plus 5 minus 6 is, oh, not minus 6, this should be, yeah, minus 6. So it's a minus 1. Okay, so plus 5 and then minus 6 is a minus 1, and that's what we get. So it actually comes out to just two things. My 0 is at x equals 1. My undefined is at x equals negative 2. And so again, we have a closed circle for the 0. So here's negative 2, here's 1. We close this circle up because we're going to include that, but we're not going to include that. And now what I would do is I would solve this here. It's probably easier. If I put negative 3 in, negative 3 minus 1 is negative, that's positive. Between negative 2 and 1, you can put 0. If you put a 0 in, you get negative. And then if you put like 2 in, you get positive. And we want positive because it's saying greater than or equal to 0. So we would say that the final answer is negative infinity up to negative 2. Again, notice how this one is not closed because it's undefined at negative 2. And then we bracket 1 and go to infinity. So again, a lot of the same stuff we've been doing. It's just that now you have to look for the undefineds when you're doing the rationals as well. But then the testing is the same. Think about the multiplicity and see how that works out. Alright, that's it for this lesson and for the unit. You guys have a test coming up, so just make sure you're working on that.